𝐿𝑜𝑏𝑎𝑐ℎ𝑒𝑒𝑣𝑠𝑘𝑖 In the previous video, we discussed double integrals over rectangular regions. Today we will continue the discussion of double integrals, but now we will be doing them over certain non-rectangular regions. More specifically, these will be regions bounded by the graphs of functions, such as, for example, this one, which is trapped between a parabola and a straight line, namely the parabola x equals y squared and the line y equals x minus 2. Now suppose that our problem is to find the value of this double integral over the region R, where R is the region at left. We'd like to solve this, and we know what the integral means, but this is different than the kinds of integrals we did last time on account of this strangely shaped region. How are we going to do it? Much in the same way, though we have to be a little bit careful. As always when doing double integrals, it is very important to have a good sketch of the region we are integrating over. Even if it's just a rectangle, it's helpful. But if it's non-rectangular, it's crucial that we have a good sketch. Well, in this case, we're given such a sketch, so we don't have to worry too much about it. Still, it will help us reason everything out, especially the all-important process of coming up with the boundaries of integration on our iterated integral. So let's see. This is what we want to compute. As I said last time, always begin your mathematical sentences by restating the subject. And the first thing we want to do is to turn this double integral into an iterated integral. But how are we going to do that? We're going to do it one dimension at a time. I'm going to begin by integrating with respect to x. That means I'm going to imagine that y is at some fixed value. So I'll put a dot right there. And if I keep the value of y fixed and change only x, I can imagine integrating just along this horizontal line right there. So far, this is like what we did last time. The only difference is that the boundaries are not so clear. And of course, they will be different for different values of y. All that means is that the boundaries of my inner integral, in my iterated integral, will themselves be functions of y. Let's see how this plays out. I'm going to start by writing my inner integral here. We always start with the inside. The heart of it is going to look like this, of course, because at every point on this blue line, I'm taking my dx, my little change in x, because that's all that's changing, and I'm attaching a weight to it. And the weight I'm attaching to it is the value of the function I'm integrating, which is, of course, 1 plus 2x. And then this integral tells me to add them all up. Okay, that's fine, but what are the boundaries of my integration going to be? Well, if I knew the value of y I was holding fixed, I could tell you what the range of x values is that I have to traverse. We've already said that those boundaries, x runs from here to here, will themselves be functions of y, because they'll be different for this value of y than they would be, say, for this value of y, where I'd be going from there to there. So at this fixed value of y, which I'm just calling y, what would the x-coordinate be where I begin my integration with respect to x? Well, this point lies on the parabola, so of course x is just going to be the square of y. So that will be my lower boundary of integration. So I start when x is y squared, and I'm going to stop when we get to this point right here. What is the value of x right there? Well, of course, it is going to depend on y. It's going to be some function of y, but that's easy to find. This point lies on this line, so that gives me the relationship between x and y for all points on that line. In particular, what is x going to be? Well, if I solve for x, I get y plus 2. So that will be my upper boundary of integration. As I move from here to here along the blue line, I'm adding up all the values of this function times dx as x runs from y squared to x equals y plus 2. Good. So this inner integral right now gives us part of what we seek. We've summed everything up just on this one line. We want this whole region, though, and we can get that quite easily, just as we did with the rectangles. This integral right here itself is a function of y. For different values of y, we're going to get a different sum when we sum it up there, or whether we sum it up here, or whether we sum it up right here. We want to add up all of those sums. We want to sum the sums. Geometrically, we're taking this little line segment that spans the gap between the two curves, and we want to sweep it out over the whole region. So we have something like that, and then we have something like that, and something like that, and something like that, and all the way up, covering the entire region. So take that inner integral, which itself is a function of y, and integrate it with respect to y as y runs from, and then the question, from where to where? Well, I need to start at whatever the y-coordinate is right there, because I'm starting by getting these very small line segments and moving up. And I will stop at whatever the y-coordinate is at that point right there. Now I know the equations of my two curves, so I could either just solve that little system of equations to get the y-coordinates there, or these happen to be so simple that you can just see what they're going to be by inspection. Namely, the coordinates of this point are 4, 2, which you can verify by seeing that they satisfy both of these equations, while the coordinates of this point are 1, minus 1. That means I'll be integrating my blue function as y runs from -1 up to 2. So those will be my limits of integration on the outer integral. And that is the way such iterated integrals will always look for problems like this. On the inner integral, the one where you are integrating along a particular line where one variable is fixed, the fixed variable may appear in the boundaries of integration. In the outer integral, where you're taking that line and just sweeping it up and down, or left to right, the boundaries of integration will always just be ordinary numbers. Anyway, let's actually compute this thing because we have not done one like it before. The process is pretty straightforward. As always, we start with the inner integral, so I will just go ahead and write this outer integral down. I'll carry the dy down later, since I don't know quite where to put it yet. As for this inner integral, the antiderivative of 1 plus 2x with respect to x is just x plus x squared, and we need to evaluate it when x is y squared and when x is y plus 2. And now I'll bring the dy down. It's very helpful, by the way, to remind yourself of which variable you are dealing with here. That's why I write x equals y squared. This kind of bookkeeping will help you keep everything straight. Well, we know how this works. I just have to plug in each value for x and do some subtraction. When I pop x equals y plus 2 into both locations of x, I get y plus 2 plus the square of y plus 2. And from that, I need to subtract y squared plus y to the fourth, which is what I get when I substitute y squared in for x. And of course, I need to bring my dy down. Well, all of this stuff is just a simple polynomial in y, and after you expand this stuff out and gather up the like terms, you should end up with 6 plus 5y minus y to the fourth, whose antiderivative is this fifth degree polynomial, and we know that thanks to the fundamental theorem of calculus, all we have to do is evaluate this thing at the two endpoints and subtract. That is just a matter of arithmetic, and when you carry it out, you should end up with 189 over 10. That's all, nothing too hard, but one question presents itself pretty naturally. When we were integrating over rectangles, we saw that we could integrate in either direction, first with respect to x and then sweep everything out through y, or first with respect to y and then sweep everything out through x. Could I do something similar in this situation? Could I have integrated with respect to y first? And the answer to that question is yes, we could have done it with respect to y first, though it's good that we didn't. It would have been more unpleasant. It is worth seeing why it would have been more unpleasant. And I quickly add that there's nothing intrinsically superior about doing it with respect to x first. There could be other problems where it's much nicer to do it with respect to y first, but often one particular way works out nicer than the other one. Anyway, let's see what would happen if we had tried to do this same integral, but first integrating with respect to y. In that case, we would be fixing some value of x and just letting y vary between the two curves. This seems like it would be straightforward enough. Integrate along one line and then sweep that line across the whole region. But there's a problem. Namely, if I fix x here, I would be integrating with respect to y over this line like that. I would be going from the line up to the parabola. And indeed, that would usually be the case. However, when we are back here, if I fix x at any point between 0 and 1, I would have a very different situation. If I fix x here, for example, then I would be integrating along this line, where I would be going from one part of the parabola to another part of the parabola. What this means is that on my inner integral, my lower boundary would be different for different parts of the region. That means I would have to actually break this thing not into one iterated integral, but into two separate iterated integrals. One adding up everything in this part of the region, and another adding up everything in this part of the region. And once we see that, if we were coming at this problem afresh, we might say, maybe it'll be better if I do it with respect to x first. And we would look at that case and see that we could do it fairly easily, as we just did. But it's worthwhile actually writing down what the two iterated integrals would look like here. It's good practice. Maybe it's worth pointing out that this double integral could be written as the sum of two other double integrals, namely the double integral of the function over this region, I'm not going to give it a new name, I'm just going to draw a picture of it, plus the double integral of the same function over this other region. There's nothing mysterious about this equation right here, as long as you remember what a double integral actually means. We're going through this region, and at every little spot, we're taking an infinitesimal bit of area, dA, weighting it with the value of the function there, and then adding them all up all over the region. All that's happening on this second half is we're doing that in two stages. First, we're adding everything up over here, and then we are adding everything up over there, and then we're going to lump them all together. So anyway, now I can take each one of these double integrals and turn them into iterated integrals. We'll take the first one first. We've said we're going to integrate with respect to y first, so we'll go over a line like this at some fixed value of x. So on this integral over that line, we'll be integrating the same old function, 1 plus 2x, dy, because we're just changing y as we move along that line. But what will the boundaries of integration be? We're going to be summing up as y runs from what to what. Of course, it's going to be a function of x, because for different values of x in that little subregion, we're going to have either shorter or longer line segments over which to integrate. Well, for any point on this parabola, we know that x and y are stitched together by this equation, x equals y squared. So in particular, if I solve for y, I get y is plus or minus root x. So that means for any particular value of x right here, I would get y equals minus root x here, and y equals plus root x here. So those would be my boundaries of integration, which I've now recorded in the usual place. And we recognize that this stuff in blue, that inner integral, is itself a function of x, because its value depends on where I froze x. That means I can integrate it with respect to x. And the only question is, what will the boundaries on this integral be? Well, that's easy, because I'm taking this blue line and just sweeping it out through this region. Starting over here, where x is 0, sweep, 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 until x is 1. So the boundaries of my outer integral will be 0 and 1. And that is the iterated integral corresponding to this double integral. Now I need to write down an iterated integral for this double integral. Same old story, but on this other little subregion. We're integrating with respect to y first, so we're imagining fixing some value of x and just letting y run through its possible range between the two curves. And as I move along that green line segment, at every little spot, I'm evaluating the function, which of course is just 1 plus 2 times the x coordinate, and multiplying by dy, since I'm just changing in the y direction. So I get 1 plus 2x dy. And of course I'm adding all of those things up, so I need to write down my boundaries. I'm adding all of them up as y runs from where to where. Well, these boundaries are going to be functions of x, because when x is over here, I'm going to get certain boundaries on y. It's going to be different when x is over here, then I'll get very different bounds on y. So my bounds on y themselves will be functions of x. But one thing is for certain, the lower boundary corresponds to a point on this straight line. And for every point on this straight line, the x and y coordinates are stitched together by that relationship right there. Y is x minus 2. That means my lower boundary is x minus 2, like that. As for the upper boundary of integration, well, now I'm on a point of the parabola. If I'm on a point on the parabola, the x and y coordinates satisfy this. So for whatever frozen value of x I have, y is going to be the square root of that x. In fact, it's going to be the positive square root of x because I'm on this top half of the parabola. So my upper boundary of integration will be the positive square root of x. Good. So now I have my inner integral, which itself is a function of x, because this gives me the value of my sum along some particular line segment, like the green one. But it's going to be different for different line segments, depending on the fixed value of x. Well, since this is a function of x, I can integrate it with respect to x. We're just thinking of taking our typical green line right here and sweeping it out across this region over which we're integrating. So we're going to start over here where x is 1, and we're going to stop over here where x is 4. So that means the boundaries of integration will be from 1 to 4. Excellent. Now we just have two iterated integrals. So we have reduced our original double integral into something that we can compute. I'm not going to carry out the details because they are pretty tedious in this case. Just as it was more of a pain to set up the iterated integrals when we insisted upon integrating with respect to y first, actually carrying out the integration is going to be more of a pain in this instance as well. It's not difficult, it's just tedious. So I'll let you enjoy that tedium on your own. Anyway, if you carry out the details, you will, of course, after some little while, arrive at the same answer, which we said was 189/10. It had better be the same answer, because both ways of calculating this integral were calculating the same thing. This number, no matter how it's calculated, is the end result of that process by which we take all those little infinitesimals, weight them with the value of the function, and add them all up. We were just adding them up in a slightly different way, but we were still adding the same things up, which is why we must ultimately arrive at the same answer. Well, that is basically the idea of doing double integrals over regions like this, trapped between the graphs of two functions. Remember always to draw a good picture of the region of integration if you aren't given one, and take a minute to consider whether you want to integrate with respect to x first or y first. In some cases, it really won't matter, like if you're integrating over a rectangle, but in other cases, it will, where it's relatively easy one way and a little more tedious the other way. There are instances in which it is actually impossible one way and possible the other. I'll show you what I mean with this next example. Suppose we're given this particular iterated integral. How are we going to evaluate it? Well, your first thought might be, this is great, it's already an iterated integral, all I have to do is grind it out. And so you get to work writing down the solution, you know you're going to just carry down the outer integral, and concentrate on what's happening on the inside integral. Well, this is an integral with respect to y. So when looking for the antiderivative, we're going to think of x as a constant. Well, that's nice, because I know that I can pull constant multiples through integrals. So I could just start by pulling this x, which I'm thinking of a constant, at least in the inner integral, through the inner integral. I can't pull it out of the second integral, but I can pull it through the first one. And the result will be this. And you're already feeling better about yourself, until you spend some time with this right here. How am I going to integrate that? What's an antiderivative for that function? The square root of x cubed plus 1. You think about it for a while. Can I think of something off the top of my head? No, I can't. You try to be clever for a while. You can't come up with anything. Can you do it by substitution? No. Maybe some weird integration by parts trick? No, you can't do that either. Is there some weird trig substitution? Nope. You twist and turn and try all sorts of tricks, and in the end you cannot come up with an antiderivative for that thing. And you rack your brains and say, what is happening to me? Have I forgotten all my basic integral calculus? No, that's not the problem at all. The problem is that this function right here does not have an elementary antiderivative. So your inability to think of an antiderivative is no shortcoming on your part. It just doesn't have one, at least not an elementary one. So you're stuck. It would seem that there is no way to proceed at all. So it would seem, but what seems to be the case is not necessarily so. Here's how we can integrate this thing. This iterated integral represents a particular double integral. Let's begin by recovering the double integral. Then once we've done that, we'll swap the order of integration so that we're doing it with respect to x first and then y, and we will find that when we do that, we are actually able to come up with the value of the double integral. Pretty sneaky. To do that, to recover the double integral, I have to recover the region, which is not given to you explicitly, although we can extract it from this boundary information. So let's recover the region. Let's draw a picture in R2. Whatever this region is, we know that we can sweep it out by first letting y run between here and here, from y equals x over 3 to y equals 2. Well, both those equations are the equations of lines. Y equals x over 3 is, of course, a line through the origin with slope 1/3, while y equals 2 obviously is just a horizontal line. And the intersection of these two lines is here at the point 6, 2. Now back to our iterated integral. We're letting y run between x over 3 and 2. So that looks like a line like this, a little vertical line. And then we're letting x sweep that line out from x equals 0 to x equals 6. So starting here at 0, sweep, 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 until we get to 6, stopping right there. So indeed, the region we are integrating over is this right triangle. Okay, will that help us? Well, let's see. We've just discovered that our iterated integral is equal to the double integral of our function over that triangle. Once again, everything is hinging on connecting a double integral to an iterated integral, though it's interesting that we've reversed the direction this time. The only reason I did that is so that I could turn this double integral into a different iterated integral, namely the integral we will get if I integrate it with respect to x first. If I fix some particular value of y and just let x vary and integrate over a line like that, and then sweep the result out, I might end up with an integral that I can actually do. Let's see. As I march along this line, at every spot I'm going to get just a little change in x dx, and I'm going to weight that with, of course, the function I want to integrate, like so. And I want to add all of these guys up as x runs from here on the y-axis all the way over to here where it hits that line. Well, to add them up means integrating as x runs from 0. That's always going to be the case. That's always going to be the starting value for x, no matter what value I've frozen y at. And I'm going to stop over at this point right here. What value of x will that be? Well, I know that that value of x is tied up with the corresponding value of y by this equation. If I solve for x, I get x is going to be 3y. So my upper boundary of integration would be 3y. And we're not surprised that it's a function of y because it depends on the value of y at which I froze everything so that I could integrate with respect to x. So this whole integral right there is a function of y, so I can integrate it with respect to y. That corresponds to taking this blue line and just sweeping it up and down through all possible values of y, from down here, where y is 0, to up here, where y is 2. So my boundaries of integration will be 0 to 2. Good. So look at what we've accomplished. I took this integral, which was originally with respect to y and then x, and by going through this intermediate, the double integral underneath it, I was able to turn it around into a double integral where first we're integrating with respect to x and then y. Now the whole purpose of doing that was in the hopes that this might be an integral that we could actually compute. Let's see. As always, we start with the inner integral. This is an integral with respect to x. And the function we're integrating, well, we have x right there, and then we've got all of this stuff, which is a function of y. Since I'm integrating with respect to x, though, I'm thinking of y as a constant. So this bit that I've circled right now, that is a constant as far as this inner integral is concerned. It's a constant multiple. That means I could pull it out through that first integral. And when I do so, I end up with this. Well, that integral is a piece of cake. The antiderivative of x is, of course, x squared over 2, and we're evaluating where x is 0 and x is 3y. Now we know that constant multiples, like this half, can be pulled through the bracket notation, so I'd end up with that constant 1/2 sitting out here, but constant multiples can, of course, also be pulled through integrals, so I could go ahead and pull that half all the way through, like that, and then when I evaluate this, I'm going to pop in 3y, and I'll get 9y squared, and then the 0 does nothing, so this whole expression is just going to become 9y squared. So we now have this, and this is a very easy integral. It's easy because the stuff under the radical right here is of such a nature that its derivative almost appears right here outside of the radical. So that means that you could probably just come up with a guess, make a few adjustments, and find the antiderivative of this thing without too much trouble. You'd start with something like x cubed plus 1 to the 3/2 power and then make some adjustments and everything should work out. Or you could do this with a simple substitution. You would let this stuff under the radical temporarily be some new variable u. Let's do it that way. So to cross this next equal sign, I'm going to let u be y cubed plus 1, which means that du would be 3y squared dy. And now we're in business because that 3y squared dy appears right here. Or at least this stuff is going to be 3 du. And now we've got our little dictionary to translate our whole integral over from the language of y to the language of u. When we do that, this thing, instead of being the square root of y cubed plus 1, becomes the square root of u. And then what about this stuff right here, 9y squared dy? Well, if we go to our dictionary, 3y squared dy is du, so 9y squared dy would be 3 times that, in other words, 3 du. So I'll put 3 du down here. Now don't forget, the easiest mistake to do with these substitutions is to forget to translate over the boundaries of integration. Here we're letting y run from 0 to 2, but now I want to see what happens when we translate over into u. Well, when y is 0, what is the corresponding value of u? Go to our dictionary here. When y is 0, u is going to be the cube of 0 plus 1, which is better known as 1. Meanwhile, when y is 2, we go to our dictionary. When y is 2, u is going to be the cube of 2 plus 1, which everybody knows is 9. And I'll have to come over here to finish this work off. I'll pull that constant multiple 3 through the integral to give us this expression. And now it's a piece of cake. The antiderivative of u to the half is u to the 3/2 times 2/3. Pull this 2/3 through the brackets. It's going to cancel with the 3/2 and give us this, which we can easily evaluate. When we put 9 in there, 9 to the 3/2 is, what is that, 3 cubed, which is 27, minus 1, so we end up with 26. And lo and behold, we have actually evaluated our iterated integral. When we initially tried it, we ended up with an integral that had no elementary antiderivative, but we were able to actually come up with the value of this integral by relating the given integral to a double integral, which we could then integrate in the opposite direction from the one we were given, and it was actually quite easy. And that is enough for today. We'll have one more video on double integrals, in which I will talk about doing double integrals in polar coordinates, and in which I will show you something really pretty, where we look at another function that has no elementary antiderivative, a more famous one, this function right here, and although it has no elementary antiderivative, I'm going to be able to show you how to find the definite integral of that function over the entire real line. Since this function has no elementary antiderivative, I cannot do this using the fundamental theorem of calculus. How will we do it? What does it have to do with double integrals? What, for that matter, does it have to do with polar coordinates, which I promised would be in the next video? Well, you will just have to wait and see. Oh, and the other mystery, what is the actual value of this integral? It's something kind of surprising. That you will see too in good time. But for now, I will take my leave from you in ancient Greek, and so say, 𝐹𝑢𝑙𝑙𝑢𝑚𝑖𝑛𝑎𝑡𝑒𝑑.